this is a kind of supplementary. In the last lecture, we learned about the direction. In terms of this upstream, that direction, the direction is from here. Think about your house. You are here, and this is network infrastructure, and this direction is called upstream. This is upstream direction, and you are receiving some file, then that is called downstream direction. Think about your application to download some video from YouTube site or Netflix. Then you want this speed, the downstream, that speed bandwidth should be much better than this upstream, right? There's usually this one is much bigger than that, sometimes similar, but this one is bigger than this upstream speed. Thus this is called not equal. Thus this asymmetric DSL, this is ADSL. Now I am trying to explain about ADSL. You are using ADSL modem here. If you are using telephone line, I'll show you later, physical media. Telephone line is like this. Actually, this one is being used in your apartment or in your household to connect your telephone to the switching equipment to go out to the central office. And you are using this one, and here that speed downstream and upstream, that speed is different. Thus this is called asymmetric. A means not. Thus ADSL, A means asymmetric. If some server in some institution that is providing some internet service, then that speed may be same sometimes, because the server should send some file and should receive some request. Then if that should be same, then that is symmetric, right? Symmetric. This is called SDSL. If that is dealing with this functionality, then that is called ADSL modem. If that is handling this functionality, then that is called SDSL modem. Those are really existing devices in the real world. Okay, I explained briefly about the direction, up, down, and is asymmetric. And let's move to the physical media. Okay, in next lecture we learned something about the physical media, but in this online it is a little bit difficult to circulate this real physical media. Actually, in the previous lecture we circulated this one. Thus you touched this one, you got some experience in terms of that physical media. Okay, I brought some physical media. First, this one is telephone line, and we can use this one to hook up telephone and ADSL modem. After that, computer through that cable modem, and this equipment. I'll show you this one first. After ADSL modem, that is providing some WAN interface. This is WAN interface. Okay, I'll show you WAN. Okay, you may see this one. That is clear enough. I don't know. WAN port. WAN port, this one is really being used, access point device. in Korean, 무선 인터넷 공유기. Access point device. This one is located here. If you are using telephone line, then another device, ADSL modem. ADSL modem is not here. After that, this is WAN port. WAN, because that is wide area network line. This is wide area network infrastructure we are using to implement, to use that the internet after interconnecting to this infrastructure. And this is WAN port, and this one, WAN port is this one here. This one is a access point device. This one, I'm showing this one. And there are other ports. Those are Ethernet ports. This one is WAN port, and that is connected to the ADSL modem here, and that will be connected to this KT or SKT or LGU plus. Those are called internet service provider infrastructure that can be hooked up to that. Make many LAN port here we can use. This one is WAN, wide area network port. The others are just LAN port, LAN. The others are LAN ports. Thus you can hook up notebook or personal computer using the Ethernet cable. That is called the LAN port. This is a wired cable. This. And you can hook up here like this, and this one can be hooked up to the personal computer or notebook if you want to use this wired Ethernet cable. But sometimes if you want to use radio frequency Wi-Fi, then this one is also providing that Wi-Fi. If you are trying to use your smartphone using that access point, then that is Wi-Fi. Then that is wireless. This one is providing that RF signal, and that will be propagated. Also, this access point is providing that capability. Okay, that's enough. And another example of these access point devices, I brought another one. Okay, let me show you. This one. This one is being used actually, and I brought here, and this is simply a power adapter providing electricity, DC power here, and this is antenna, and this is also providing that WAN port here. WAN, you can see, right? WAN. This is, as I mentioned already, connected to this ADSL modem, or if we are using cable modem, then cable modem. That is providing that WAN interface, then that will be hooked up here. After that, the others are just a LAN port, wired Ethernet port. And this one is providing the Wi-Fi LAN, wireless LAN. Okay, that's enough about this one. And let's move to the other physical media after laying down here. Okay. And I just introduced Ethernet cable. This is the Ethernet cable, most common. This is called Ethernet connector. That is called registered jack 45. This means registered jack 45. Your telephone jack, usually that is called registered jack RJ11. That is thinner than this one. This one is thicker, and the 8 lines can be here. And later in other chapter we will learn how to make this one. But today we want to see just physical media, and this one is a kind of that physical media, Ethernet cable and Ethernet connector. And if we are cutting that, then you can see 4 pairs of Ethernet cable here. Let me show you another one also. Okay, here, same on Ethernet cable, same on 4 pairs, right? That means 8 nines, 4 pairs, 8 nines, 4 pairs. Thus, Ethernet cable is consist of that there 8 nines, 4 pairs, and this one is not shielded, not shielded, unshielded. And as you can observe here, that is twisted. You can see that is twisted, right? Twisted, unshielded, twisted cable. Okay, this is called UT unshielded twist pair, and this is using this UTP, that acronym that is more common. This is called UTP cable, most common in the world for Ethernet cable. And this one is category 5. There are different kinds of categories, and this category 5 is most common and economic. Category 6, as shown in the previous PowerPoint slide, that speed is a little bit higher than this, because that is a little bit more expensive, and that is shielded. If shielded means that is some the grid of the noise protection shield grid, that is shielding, that is protecting from noise interruption. Thus, this one is more economic, and that means cheaper than this category 6, and this one usually you can use around until 100 meter. Thus, within that distance we can use this one for our Ethernet connection cable. Okay, another one. Instead of that, this is optical cable. This is so thin, thus it seems like hair. I brought another one here, like my hair, and dyed hair, that is colored hair, like this. And this speed is gigabps, and if that is final one in terms of that purity, then that is providing terabps speed, much higher speed than previous Ethernet cable. Previous Ethernet cable is using copper wire, but this one is glass fiber. Optical fiber. This is called optical fiber. Around the 1970s, as I mentioned, Corningware, that is making some manufacturing cooking equipment, bowl and dish, and they are dealing with many different kinds of glasses. Thus, they are very familiar to this glass related products. Thus, they made this optical fiber first time in the world with very high purity, and that means the speed is much better, higher than the copper wire, and also it is continuously being evolved and developed. Thus many different infrastructure for interconnecting through the ocean, the transatlantic, transpacific, this optical cable, optical fiber that is being used, because that the signal can go to far, to go to transmitted far away. But if we are using copper wire, then we should some repeater to amplify again and again. But if we are using fiber, then we don't need to use that many repeaters. Instead of that, we can use this less than this. Then it can, that means it can transmit it further. Okay, those are optical fibers example. Okay, you can see, I will show you, very thin, because it is not clear to look at in remote site. And there are many different kinds of the optical fiber, and that inside of this is optical fiber, and that is the connector to provide some proper interface, and that can be used to hook up to the optical fiber equipment. Both ends can be used. Okay, those are optical fiber. And another example, last time we learned about coaxial cable. This is coaxial cable. This is, okay, this one is copper wire, and this one is coax. And here the signal that is transmitted through this copper wire. This is much thicker than the previous Ethernet cable. I'll show you. You can compare. Okay, you can see the thickness. It may not clear enough, but you can compare. Thus, that means this is transmitting broadband signal. In terms of frequency range spectrum, that is much higher than that. Thus, usually think about our cable TV in your house. If you are subscribing cable TV, then that is, okay, I will erase this one first. The bandwidth. The bandwidth is very important, like our express highway. Depending upon the size, width, that is called analog example of this electrical bandwidth. Usually this bandwidth of this one is for this cable TV in your household around 500 megahertz. Usually for analog channel like YTN, MBC or MBN or many other channels, TV channels, that is taking 6 megahertz in terms of analog signal. Usually we are using now digital signal. We are considering the previous case, and after that I will move to the current technology, digital technology, and this one is analog signal. Then if we are dividing this one, then like this, the different channels, around over 70 channels, and some channels for control signal. If we are using analog channel, then it is limited to this number of channels. But if we are using digital signal, then this one is carrying more channels because digital signal is providing better capability, and it is consuming narrow bandwidth than analog signal, analog technology. Thus, we can enjoy a couple of hundred channels even with this same coaxial cable because of that digital technology advantage. Okay, let's move. Today I am just briefly introducing physical media. Okay, this is the same one. Thus I will finish. Okay, this one can be hooked up like this, and this one can be hooked up here like that, like your cable TV channel interface in your house. Okay, that's enough to understand this physical media. Later I may introduce again, and today I will finish of this physical media introduction. Okay, before finishing this one, I will show you another one for the supplementary introduction. Let's move to this web page. Okay, now it is working. Okay, I am showing a Cisco switch. This is Ethernet switch. All of them. Those are Ethernet switches manufactured by Cisco. You can see this Cisco logo is here. Cisco is that company, Cisco. That company is established around 1984, around that time. Some students, graduate students of the Stanford University, they established this company, and they made their company name after this San Francisco, but they eliminated this one to make it more simplified. And you can see that logo, that is Golden Gate Bridge. It seems like that bridge, right? And that is logo of Cisco, Golden Gate Bridge. Thus you can see this one clearly. Okay, this one is very big company, and in terms of this computer network, and especially router switch, Ethernet switch, and the next one is about the router. The router is like this. Actually, I circulated this router in last lecture, in the previous lectures, but in this semester, unfortunately, because of the COVID-19, we cannot use offline lecture. Thus, I am showing this image instead of that. Those are routers. Those are bolts and nuts of this internet infrastructure. And there are many different kinds in terms of that capability and their functionality and the speed and also the price. Those are different. There are many different kind of router equipment, and those are manufactured by Cisco, and the Cisco is one of the major router manufacturing company. And this we learn subchapter 1.3. That is about network core, explaining about packet switching, circuit switching, and network structure. About the network core, that is a kind of mesh of interconnected routers. As we observed already in the previous lecture, this is the router symbol, and the infrastructure is composed of this kind of routers. And the packet switching concept is important here because the datagram and the data, that is a chunk of data, and that is called the packet. This one is switching, that means exchanging that the packet to arrive in the final destination. And there's this host is breaking application layer messages into packets, forwarding packets from one router to the next across links one path from source to destination. And each packet is transmitted at full link capacity. This one is the link. There are many different kinds of links, and to arrive at the final destination, that packet goes through that many different kinds of links. First, let's look at this packet switching concept about store and forward. In terms of packet, that should be stored in the memory during that journey to the final destination, and that should be forwarded through that link. But let's focus only one single router. Then here L bits per packet, and that is transmitted through this link. The speed is R, bit per second, and this is router. After storing, and that will be forwarded through this link. Also, that speed is assumed as R bps. And how long does it take in terms of the speed delay time? It takes L over R seconds, because that length is L bit and the speed is R bps. Thus the speed delay time will be like this, L over R seconds, to transmit L bit packet into link at R bps. And this one is storing and forward. That is a kind of main role or functionality of this router, and yeah, we learn about this router's functionality later. Entire packet must arrive at router before it can be transmitted on next link, because there are many different kinds of links that may be, and also even though we are using single line, there are a sequence of data stream, and that should be stored first before transmitting to the next destination. Thus here we can calculate the delay time. We are assuming this is very simplified example, and here we have two links. Each link it will take L over R, thus it will take 2 times if we are assuming zero propagation delay. And here, if we are using real numeric number here, L is 7.5 bps, R is 1.5 mega bps. If you are calculating, then please calculate together the units together. Then we can find out the final unit. Here 1/2 transmission delay will be, if we are dividing this one with this 1.5 megabps. Megabps means megabit per second. Thus finally, if after dividing this one, that the second will come out. That is the final unit, the 5 second delay time. Still, we are learning about packet switching, and one of the main functionality of packet switching, that is queuing and delay. Queuing means that is storing and wait, and it will take time. And here, if that size is limited, then there may be some drop, packet drop, and anyhow we will look at that later, but let's focus on this one first. we are assuming R is 100 megabps, and here this link speed is slower than this incoming rate, than 1.5 megabps. Let's assuming that real number. Here then that will be waited. That packet will be waiting here. That is called queue. Queue means waiting buffer. Queue of packets waiting for open link, because there are so many different packets waiting for transmission. Thus here we can think about the loss. If arrival rate to link exceeds transmission rate of link for a period of time, then packets will wait. That will be queued. That means wait to be transmitted one link. And the packets can be dropped if the memory, there's no memory. If the memory is consumed up or filled up, then that packet should be lost. That will be dropped. That is called queuing delay and loss. Queuing and loss. Here we'll learn about the two key network core functions. Those are all implemented in the router, and only functionality is routing functionality. Here this one is determining source destination route taken by packets, and how this routing algorithm is handling that. Depending upon that routing algorithm, this final destination, depending upon that, the final destination is in the IP address of the final destination. Depending upon that, the output link will be decided. And the routing algorithm is doing that for better transmission through that router. And if we are looking at microscopically in the router, in this specific router, then that function is forwarding function. This one is moving packet from router's input to appropriate route output. That is forwarding functionality of this router. But routing functionality is overall functionality, considering the whole journey to the final destination. That is a big difference from this forwarding. If we are considering the circuit switching, previous example was packet switching. Actually, we are using that packet switching technology for our internet packet switching. But a long time ago, the circuit switching that is being used, that have been used for telephone switching since at the early of 20th century, just at the beginning of the telephone technology that is introduced in the world. We need some switching, and that technology is circuit switching. This one is end-to-end resources allocated to reserve the call between source and destination. Instead of this computer, let's think about your telephone, because the telephone was the original equipment here. The later computer was introduced. Thus, using that telephone switching infrastructure, we are using this transmission of the computer data through that circuit switching. If we are using this circuit switching, then that should be called first, as we call first for our telephone call, exactly same way. After that, we can talk like that. After establishment of that call setup, we can send the computer data. In diagram here, each link has 4 circuits. 1, 2, 3, 4. 1, 2, 3, 4. And all gets second circuit. Let's assume all gets second circuit here. First one, second one, in top link, and the first one in the this link. And finally, that will be arrived to the final destination. And this one, each link is dedicated in this circuit switching technology. This is dedicated resources, no sharing. That is main disadvantage of this circuit switching. And this one is circuit-like. And if we are using this circuit switching, then that resource is reserved already. Thus, that the performance is guaranteed. Like our railroad transmission, railroad, if we are comparing to the car in the expressway, then railroad traffic, that will be more guaranteed, right, in terms of the performance in the total delay time to arrive. Circuit segment, if that is idle, then if not used by core, then still it is not being used. That is loss, waste. That is main disadvantage of this circuit switching. This one is being used commonly in traditional telephone network, and this one is the old one, and that was available even before packet switching technology. And here, okay, let's move to here. Okay, so this one is comparing FDM technology versus TDM technology of the circuit switching, because we can implement in this way or in this way. And this one is using frequency division. This one is dividing frequency spectrum into like this. Different frequency spectrum, different frequency range. Like our real example of this FM radio station or TV, they are occupying some frequency range that is preoccupied already, reserved. And per user is, that means per FM radio station that they are using, or per television, TV channels are using exclusively. If we are considering time division multiplexing, here M means multiplexing. Multiplexing concept will be explained later. Anyhow, if we are trying to share single resource, then that is called multiplexing. Many users are trying to use the single resource, then we should share. And how we can share? And in this frequency, depending upon that frequency range, we can share, or depending upon time slice that can be shared, like this. Actually, this one is occupied, thus exclusively each one is using that single first one, second one, third one. And if we are considering our telephone call, then our voice, that is sliced packet, sliced voice, that data is being sent here, and the next data, our voice, that is, I can say, that is voice data that will be transferred, and finally we can hear with our telephone. That is TDM technology. This one is explained about the technology for the circuit switching, and depending upon frequency, depending upon time division, we can implement. And here we can compare the packet switching, mainly that is being used for our internet technology, and circuit switching, mainly that have been used for telephone switching, and that is newly introduced, and that is very helpful to solve the internet traffic. And this one is trying to explain about that. Packet switching allows more users to use network. Here, let's assume 1 megabps link here, and each user is consuming 100 kbps, and active only 10% of time. But circuit switching, if we are using circuit switching, then each user is fully occupying each exclusively assigned channel. Even though he is not using, that will be occupied. Thus, the other user cannot use. But packet switching, like our express highway, your car is considered analogously, as an analogous example, packet. If you are not using that, then other car can utilize that highway. Here, depending upon the probability, you don't need to worry about this probability at this moment. Just simply think about these number of users, and if that is not fully used, sometimes that user will use that highway like that. You don't need to worry about that probability at this moment. That means randomly that is being used, then the supportable full user number of user will be much bigger than this number. If each user is occupying the resource, like this circuit switching concept is that, as we learned in the previous slide. But packet switching, that is shared with other user, like the highway shared with our other car. Then more cars can utilize that highway. Even though that is not exactly the same, you can think about the analogous example. This circuit switching is similar to the railroad transmission, and packet switching, you can think about the highway for car traffic. Then that is a kind of analogous example. Still, we are comparing packet switching versus circuit switching, because this one is a traditional technology introduced long time ago, since the first introduction of telephone at the early of 19th century. Actually 20th century, 1900 some year. And even though that the telephone was introduced the year of 1876 by Alexander Graham Bell, later the switching equipment was developed and introduced at the beginning of around 1900. That means 20th century, at the beginning of 20th century. Okay, packet switching, that is introduced around the year of 1960. Thus, after 60 years, almost 50 or 60 years, that is introduced first time. There's new technology comparing to this circuit switching. Thus, we are comparing the disadvantage and the advantage of them. Then this packet switching is very good, excellent, slam dunk winner, and that may be good for some case, but that is not so good for some other case. This is great for bursty data. Fortunately, our computer data is bursty data, and the resource sharing and the simpler local setup. That is main advantage of this packet switching. But the main disadvantage of this packet switching is if there is some excessive congestion is that may be possible, then the packet delay and loss that is so serious, like our highway, if there is some traffic jam, like Thanksgiving holiday, then that is overloaded, then that is called excessive congestion. In that case, protocols needed for reliable data transfer, congestion control. Why we need this protocol? Later we learn about this one. Because this protocol is trying to solve this problem. We learn anyhow later in detail about that. How to provide a circuit-like behavior. But circuit technology, this circuit switching technology is not so good, but this one has some advantage that is providing some guaranteed delay time. Then how to provide that good aspects of the circuit-like behavior. Here, bandwidth guaranteed, that is guarantees needed for audio video applications. Packet switching is not providing that guaranteed bandwidth, then circuit-like behavior, that will be good, because this is real-time data that is requiring that. And still that is studied and researched, but most of them is solved, thus we are enjoying the audio video application. Those are called multimedia application. Here, human analogies of reserved resources, circuit switching versus on-demand allocation packet switching. As I explained already, if we are reserving some resource, then that is similar to the circuit switching. If we are sharing with others, and we are using that based on demand, that is called on-demand allocation, then that is similar to this packet switching. Okay, let's think about this internet structure. We are in this chapter, that is the very first beginning chapter. Thus, we are trying to get some overall picture to understand the whole image about the internet and the computer network. Internet, that is called, in other way, network of networks. Here, this network is single network, but inside of that is composed of many different kinds of heterogeneous networks. Thus, this is called network of networks. And the systems connect to internet by access internet service providers. Think about your SKT or KT or LG Plus. Those are all internet service providers. And access internet service providers in turn must be interconnected. They are not isolated. Each different internet service provider, even in Korea, a domestic internet service provider, in the outside, like in the United States, Bell Atlantic, Pacific Bell, and so on. Those internet service providers are all interconnected, so that any two hosts can send packets to each other, even in our domestic network. That is same from SKT, from SKT to KT or to the LG Plus. They are interconnected. Resulting network of networks is very complex because of that interconnection of different heterogeneous internet service provider and networks. Evolution was driven by economics and national policies. And let's take a stepwise approach to describe current internet structure like this. Let's assume different network, how to interconnect. And this one is the first model we can think we can imagine and how that can be implemented. And this one is the very first concept to explain our final infrastructure. Option is connect each access internet service provider to every other access internet service provider. In this way, if we are trying to interconnect, then the order of complexity that will be so complicated, because each one they should be interconnected point to point in this way. That is not effective, not efficient, and we should think about this instead of the previous slide. This global internet service provider is interconnecting them together, and inside here this traffic data that it can be routed to other internet service provider through this core global internet service provider. Option is connect each internet service provider to one global transit internet service provider like this. Customer and the provider, internet service providers have economic agreement, and that can be divided like that, but still this one can be shared with other access network here regionally, also in this region or this country or this area, and they will be hooked up together. Inside they will be interconnected. Then that will be more effective. This is called Internet Exchange Point. This is the model which we are using. And there may be many regional networks depending upon that their business. And depending upon their service provider, or depending upon the major internet business company like Google, they can provide this content providing network. Okay, this is the internet structure network. As I mentioned, this internet is a kind of network of networks. Thus hierarchically, this one is tier 1, and Google can be one of these tiers, and they can provide its own infrastructure like this to provide a good service for Google users. And here this is access internet service providers like KT or SK Telecom or Bell Atlantic in the United States, or Southwestern Bell or Pacific Bell, like that. And center small number of well-connected large networks. And tier 1, that is commercial internet service providers. Level 3, Sprint and AT&T, NTT. Yeah, this one is Japan, Japanese, like a KT, Nippon Telephone and Telegraph, national and international coverage. And this content providing network, like a Google is providing the worldwide global service. There's a private network that connects data centers to internet, often bypassing the other tiers to provide a better service, to provide YouTube or Google search engine service. Also Microsoft network, also Azure. Okay, we'll look at those cloud services later. Tier 1 internet service provider, for example, this is Sprint case, and they are interconnected like this. This is in the United States. Here, if we are looking at one single site here, that is called the POP. POP means point of presence, like our central office for our telephone switching. To from backbone in terms of the internet packet switching, this one is providing this infrastructure. Okay, let's move to the other topic. This one is about the performance issue that is about delay time and loss rate and throughput in networks. Let's think about this loss and delay. Why that is happening? Packet queue, as I mentioned already, packet is traversing through that router, and the router has limited memory size. If that data is arriving more than that memory size, then that will be dropped. That is loss. And the other packets stored there, they should wait to use that shared link. Okay, let's follow this one. Packet queue in router buffers and packet arrival rate to link. If that is exceeding open link capacity, that is arriving more than departing packets. Then packets that will be queued, that will be waited in this waiting buffer. And waiting for transmission. Here, and it will take time to be transmitted. And also there is another factor in terms of delay time, that is queuing delay time. And also another time we learn about that 4 factors in terms of that delay, even though we observed the 2 factors in the previous slide. Here we have 4 factors. One is processing delay. Here deep processing, that is nodal processing. This is router. Think about this one is a kind of special purpose computer that is sending the transmitting packet. First it is receiving, and it will wait there, and it is going out. And it takes time. That is called nodal processing delay. And this one is checking bit error, whether there is some error or not. It is checking depending upon the protocol. It is handling that. And determining open link, which link, there may be some other link depending upon the final destination. Usually that will be lower than a millisecond range. Another factor, queuing delay, as I mentioned already, and this is the time waiting at open link for transmission. Depending upon the congestion level of router, that may be different. Thus, this one is variable delay time. And another delay time in next slide we'll look at. Here another one is transmission delay. And depending upon link speed, it will take time. That is called transmission delay. Thus, depending upon the speed, link speed, that is R, and depending upon the size of the packet, it will take time. That is called transmission delay. Here, another final delay factor is propagation delay. Depending upon the media speed, even though that is transmitted in the light speed, it is not exactly same to that light speed. It is almost, but depending upon the media, then may be different slightly, but near to the light speed. If we are dividing that distance and how long does it take to propagate from here to here, with this speed, it is almost like the light speed, then that is called the propagation delay time. And now we have some homework assignment, and you can understand better after solving that question. Caravan analogy. If we are considering this caravan, this is a kind of packet, and instead of explaining directly that packet, it is first time to study this one. Thus, this one is showing some analogous example. Each one is bit, and that is packet. Let's assume the 10-bit packet is arriving here, and that is one router, and to the next router, this is communication link. This is analogous example, and we are assuming this one is a highway. And these cars propagate at this speed, and these toll booths, it will take 12 seconds, we are assuming, to service a car. And the car, we can assume this is a kind of analogous example. This you can think this one as bit, and the caravan, this one is aggregated bit, and that is packet. Then we can think how long does it take to be transmitted to here, lined up here. Thus this one is serviced here. After that, that is driving here, and finally that will lined up here. Then how long does it take? We can calculate this one. Thus we can understand better about that packet transmission delay time. Time to push entire caravan through toll booth, each one, it will take 12 seconds, and now 10 cars, thus 120 cars. That is so simple. And we should add up another driving time here, from here to here. That is propagation, similar to the propagation delay in our previous 4 delay factors. And the second toll booth before that, those are lined up here, and they should drive here. And each one is driving. The speed is 100 km per hour. Thus each car will take 1 hour. If we are simply dividing this one, then 1 hour. Then this one is 60 minutes, and this one is 2 seconds. Actually, this one is 120 seconds. That means 2 minutes. Thus, if we are adding up together, then 62 minutes will be the added up final delay time. If we are considering other example due to different speed, different lengths, and let's assume the car can propagate. This one is almost airplane speed, and anyhow we are assuming 1,000 km per hour. And suppose toll booths now take 1 minute to service the car, and it will take 1 minute. And then the question is, will cars arrive to second booth? That is different from the previous question. Second booth, before all cars serviced at first booth. Okay, the answer is S. Still, this question is in other way we can think. Still, some cars, some bits are still remaining here, even though that the remaining of cars of bits or bits, first one is arriving there. There's whole links are occupied, and still some cars are here. That is possible. The answer is yes. And let's think about this case. Okay, this one is not showing other slide. So let's think about this. Okay, 1,000 kilometer, and the speed is, and it will take, if we are dividing this one, then it will take 1/10. If we are dividing 100 kilometer into this 1,000 kilometer, then 1/10. That means 6 minutes from here to here. But it should be serviced here. It will take 1 minute. Thus, 1 minute plus 6 minutes, it will take 7 minutes. Still, the others are still remaining there. 3 cars are still remaining there after 7 minutes. Okay, let's look at this queuing delay. Queuing delay, this one is a little bit difficult concept in the bachelor degree. And usually that is being studied in the graduate school. And let's assume this is if that this one is a little bit difficult in the undergraduate course, but if we are considering some general concept instead of the microscopic detailed analysis, then that will be easy to understand. Let's assume this R is the bandwidth and the speed, that unit is bit per second, and L is the length, that unit is bits, and A is the average packet arrival rate. How many packets are arriving per second, like that. Then if that is so low, that means this speed is much higher than that arriving speed, then queuing delay will be small. Think about our expressway. Randomly, the cars are arriving there. There is not many cars arriving there, and this one can be used by this single car. Then the queuing delay will be very low, almost zero, like this. But if that is approaching to 1, like this is LA over R. That is much higher than this. This is approaching to that, like this. Then the delay time will be increased a lot, like this. Let's think about this toll gate, and many cars are arriving, like Jungbu Expressway or Gyeongbu Expressway Highway, at the toll gate, and they are departing there. And so many cars are arriving there, like Thanksgiving holiday season. Then that highway will be almost like parking lot. And if that is much more than that speed, the arrival cars are so many cars, then that delay will be almost infinite. The traffic jam is so serious and almost parked there.